Welcome. This video will show how a hardware-accelerated crypto device can be used by a containerized application running in a confidential computing environment. The crypto device is an IBM Crypto Express coprocessor in an IBM LinuxONE 4 system. A logical partition is running the KVM hypervisor, which is part of SUSE Linux Enterprise Server 15 Service Pack 6. A virtual machine is started in confidential computing mode, which IBM refers to as secure execution, using the IBM Hyper Protect container runtime. The container runtime will download a Node.js containerized application built using a SUSE Linux Enterprise-based container image. A specific IBM Crypto Express coprocessor card and domain is passed through the container runtime and available to be used by the containerized application. This demo assumes you have basic familiarity with setting up the confidential computing environment, building a containerized application, and running the containerized application in the confidential computing environment. The technical reference documentation titled Confidential Computing with SUSE Linux Enterprise-based Container Images using the IBM Hyper Protect platform is available at SUSE.com for step-by-step details. The demo begins on the SUSE Linux Enterprise Server KVM host running in a LPAR on an IBM LinuxONE 4 system. The LinuxONE 4 hardware administrator has assigned the IBM Crypto Express card with number 0 and domain with number 32 to this LPAR. The lszcrypt command shows the information about the card and the domain. The hardware administrator had to initialize the domain in enterprise PKCS number 11, also known as EP11 mode, with a master key. The master key verification pattern is being saved to confirm the domain with its key is the same when used by the containerized application. Let's demonstrate the containerized application by starting it with Podman. At this time, the containerized application is not running in a VM or in a confidential computing environment. Executing the same commands as in the terminal confirms the application can see the crypto domain, card, and master key verification pattern that was shown in the terminal. A contract must be created to execute the containerized application in the container runtime. The Docker Compose file points to the containerized application, which was built using a SUSE Linux Enterprise-based container image. The base64 encoded file representing the Docker Compose YAML file is being regenerated. Both contracts, one that passes the crypto device into the container and the other that does not, are being searched by grep. Grep is used to confirm that the contracts contain the correct Docker Compose YAML definition. The QCOW2 file for the virtual machine will use version 25.1.0 of the IBM Hyper Protect confidential container runtime. There are two virt-install scripts similar to the contracts, one that passes the crypto device into the VM and the container through the --host dev option, and the other that does not. Let's use the contract that does not pass the crypto device to show that the container will not see the crypto device. The init-disk is being regenerated with make-isofs so that it includes the contract that does not pass the crypto device. Now let's start the VM with the virt-install script that does not pass the crypto device. The console output is being shown as the container runtime is started. We will switch to the rsyslog screen to look at the logging information captured, which shows the container was pulled from the github.io registry and started. Switching back to the Hyper Protect container runtime crypto pass-through screen, we know that the container is running successfully when we see the message, VSI has started successfully. The containerized application is now running in the confidential computing container runtime. Refreshing the browser reconnects to the containerized application. Executing lszcrypt and looking for the master key verification pattern file produce errors which confirms that the crypto device has not been passed. Time to kill the VM so we can try again, but with the crypto device being passed. To pass the crypto device, it must be released from the KVM host, which is done with the echo commands. We can see the release was successful because the domain has no driver associated and no master key verification pattern file exists. The kernel module for the virtual function IO AP driver is being loaded, which will allow the Crypto Express card and domain to be available to KVM guests using the VFIO mediated device framework. The IBM Crypto Pass-Through documentation requires a UUID be created and assigned to the VFIO AP kernel module, and the Crypto Express card and domain are assigned to the UUID. The versh command can be used to find the exact name of the node device by searching for the UUID. This name is copied and added to the -- hostdev option in the virt-install command. Let's use diff to compare the contracts to see the additional lines that are required to pass the crypto device to the containerized application via the container runtime. The IBM Crypto Pass-Through documentation provides options, secret and PV-secret, to pass the crypto device details. This demo is using the secret option for simplification. The container bootstrap will transparently execute the PV-secret using IBM validated and curated code. Using the PV-secret option requires additional effort by a relying party. Using PV-secret provides additional security because the attestation request and result are created and validated by the relying party rather than by IBM provided bootstrap code. Let's copy the contract to user-data that will pass the crypto device. The init-disk is being regenerated with make ISOFS like before, but with the contract that will pass the crypto device. Now let's start the VM with the virt-install script that passes the crypto device. The console output is being shown as the container runtime is started. New messages are displayed about loading the crypto drivers and adding the secret. We switched to the rlog screen to look at the logging information captured, which shows the container was pulled from the github.io registry and started. Switching back to the HPCR crypto pass-through screen, we see the container is running successfully based on the VSI has started successfully message. The containerized application is running once again in the confidential computing container runtime, and a refresh of the browser reconnects to the containerized application. Executing lszcrypt and looking for the master key verification pattern file works this time. Let's compare the master key verification pattern seen within the container with the pattern that we saved earlier. Using grep to search for the pattern in the file proves that the key has not been changed. This video has shown how a hardware-accelerated crypto device can be used by a containerized application running in a confidential computing environment. Specifically, an IBM Crypto Express coprocessor card and domain were passed through the IBM Hyper Protect container runtime and made available to be used by the containerized application that was built on a SUSE Linux Enterprise-based container image. Check out the technical reference documentation titled Confidential Computing with SUSE Linux Enterprise-based container images using the IBM Hyper Protect platform at SUSE.com for all of the step-by-step details. Thank you for your time.